Hey everybody, welcome back to the channel. As you probably read already in the title, today we're going to be discussing the unsung hero of the tool and cutter grinding shop, the noble grinding wheel. Now I do want to be clear here, I'm not giving you guys advice, I'm not telling you how to do anything. All I'm doing is simply sharing my own personal experiences. And so when it comes to the safe handling of any of this stuff, follow the manufacturer's recommend, don't follow me, okay? This is just my own personal experience. So we're not going to be discussing every single aspect of every kind of grinding wheel today. There's just too many. I figured just to keep things simple, I would keep it limited to what I actually have on hand here in my shop. I've got this little sort of grid set up here where the columns of the grid are the abrasive type of the wheel and the rows of the grid are the style of the grinding wheel. This first column here is aluminum oxide. I mostly use that for grinding high-speed steel, but it would also be my go-to for grinding any metal that I have to grind here in the shop. The second is silicon carbide, and it is for grinding carbide. I don't particularly like it because the wheels degrade very quickly and it's super tough to get a good finish. Third column here is my diamond wheels. They're also designed for the grinding of carbide, and you can get a much better finish, and if taken care of, they last much longer. So row number one here is my plain style wheels, and they're meant to do their grinding on the outside. So I'll do surface grinding with these, I'll do cylindrical grinding with these, the grinding of tapers, essentially just about anything round you would be using this plain style wheel. This row is my cups. I have both flaring cups that flare, as you can see, and straight cups, which are straight. They don't have those same angles on them. The flaring cup is meant to do all of its cutting just on the very outer edge here. So the whole time you're using it, you need to maintain a clearance angle in here. And that cuts down on the heat and makes it cut much more freely. The straight cup does not have a clearance angle, and so when you're using it, you will be using this entire surface. So you just have to make sure that you're using this for the appropriate task. And then down here I have this last row with only one in it is my dish wheel. It also has a clearance here because it's meant to only cut on the very outer edge. Also with this wheel, you can shape them and you can plunge with them. And that makes them handy for doing certain work. Regardless of the abrasive type or the shape, all of these wheels are available in a wide variety of grits. And just in case someone doesn't know, with grits, the higher the number, the smaller the particles and the finer the cut. The lower the number, the bigger the particles and the coarser the cut. So when it comes to grit size, from what I gather, this is somewhat of a standard across the industry, where if you took a 1-inch space and you took some particles of grit, all the same size as each other, and lined them up side by side until they filled that 1-inch space, however many you could fit in there would be your grit size. So in this example, I've got 14 little grit pieces here, and you can see these are about half the size, and I've got 28 of them there. This explanation appears to explain what I see in front of me here pretty darn well. But if I'm wrong here, or if there's significantly more to it, please put that in the comments, enlighten us all. I'd sure like to know if I'm missing anything when it comes to grit size of these grinding wheels. When it comes to grit size, generally speaking, you're going to want a coarser grit when there's a lot of materials to remove. If you're worried about creating heat, you'll get a lot less heat. You will get more deterioration of the wheel more quickly. When it comes to a fine grinding wheel, a fine grit, you can achieve much better surface finishes. It will generate more heat, and you will not be able to remove as much material as quickly as you could with a coarse wheel. So when you're talking about surface finish now, there are other factors that affect it besides the size of the grit you have. The speed at which you are rotating your wheel also plays a factor. Spinning your wheel more quickly will give you a finer finish. It will also generate more heat. And spinning your wheel more slowly, generate less heat and give you a worse finish, but will allow you to basically hog material off more quickly. Even beyond the speed of the wheel, there's also the dressing of the wheel. And when I say the dressing of the wheel, we're going to talk about dressing more in the future here shortly, but it's running a diamond or a number of diamonds past your wheel to expose fresh edges. So now, if I have a wheel and I dress it very, very slowly, essentially that will dull the wheel, kind of close its pores. That will cause it to act as though it was a much finer wheel. It will allow a better finish, but it will generate more heat. And the opposite, if you dress it very quickly, that will expose a lot of fresh cutting edges. It'll really sharpen the wheel and it will bring that porosity back, and now it will cut more coolly. So you can adjust your surface finish even if you only had one grinding wheel to work with. I have a couple examples here of wheels that I've dressed. Now, I've dressed them with this. It's a little metal bit with particles of diamond impregnated in it. And when the wheel's spinning, you just simply, do what you want and you'll get it. And so hand bombed a radius on here. Can't remember what for, but I can certainly tell it was hand bombed. So I would have been using one of these guys. This wheel here, I was having a clearance issue. So I hand bombed a little 45 on the one edge of it there, just to give myself some more clearance for the thing I was doing at the time. This is a wheel I was creating a thread comb type of thing for someone once upon a time. And so I gave this a 60-degree edge so that I could create this thread comb. So at the time I made this, I was actually trying to do some precise work. So I wouldn't have hand bombed it. I would have used the machine, the graduations on the machine, tilted the head from side to side to get this bang on exact. But since then, it's been handy for different things. And just as the point of it wears down, I've just been hand bombing it back just to give myself a point. So in recent times, I haven't been using it as a 60-degree thread cutting wheel. I've just been using it as a pointy wheel. When it comes to the dressing of and shaping of wheels, there's a lot of different tools at our disposal to do that. If, let's say, for example, we want a radiused wheel, we can make the face of a wheel either concave or convex. And basically, we would take our radius grinding fixture, take one of our dressing tools, diamond dressing tools, mount it on there, touch off our center, and then if we wanted the wheel face to be concave, we would run this past center by the appropriate amount. And if we wanted the face of this wheel to be convex, we would run this back from center by the appropriate amount. We're also able to choose where we put the radius on the wheel. So we can center it if we want, just simply by centering the whole radius grinding fixture to the wheel. And we could, if we want to, we can give ourselves a nice 180-degree radius. Let's say we only wanted a 90-degree radius from the edge here around to down here. We could do that by touching off on this edge with the radius grinding fixture, and that would give us just a 90-degree radius, both convex and concave, depending on where we position our diamond dressing tool. Now, when it comes to grinding a convex face on a wheel, you can imagine this great big wide multi-diamond head. I mean, you're not going to be able to get a very tight radius in there, and that's what this little guy's for. It has just one little speck of diamond in the center of it. You can dial that in and out before center and after center, and then you can run it past your wheel by rotating it like this. Mostly I use this for really tight convex radiuses. When we have a plain style wheel here, if we want it dressed true to the travel of the table, that's easy enough to do. We can mount our diamond dresser to the table and just bring it past the wheel. We can also offset the wheel to different angles based on this graduated scale here, and then we can carve different angles into the wheel. And now here's an example of a wheel that I've done that to. And in this particular instance, the reason I did it was I wanted to grind on the diameter of the wheel, and I wanted to grind an angle into this drill bit. And this allowed me to grind the diameter and the angled part all at the same time, which was handy. One of the advantages of doing that was it left me with like absolutely no transition along this area where this diameter meets this angle. And if I went at this in two different operations with two different wheels, it would be much more difficult to get zero transition in this transition area. And if you're interested in seeing the video where we made this wheel or modified this wheel and modified this drill bit, I'll leave a link in the description or put a thing up at the end, or I'll do something like that. Now that we've talked about the dressing of silicon carbide and aluminum oxide wheels, we're going to talk about the dressing of the diamond wheels. Now, it's not dressing in the same way. We are not trying to change the shape of the diamond wheel. That gets very expensive very fast. You can do it by grinding steel, and grinding the steel just tortures the diamond, and it'll, you know, if you focus the grinding where you want the diamond to be gone, it'll eventually go, but you really want to limit that. It's better to use the appropriate style of wheel and just be happy with the form that your wheel has. However, you can dress your wheel as in sharpening it. And the way we actually do that is we take a stick of aluminum oxide, and while the wheel's spinning, we just feed it into the wheel. You can see I've done that here on something. And what that does is it opens the pores back up, it releases all of the trapped carbide, and makes the wheel cut more freely and cooler. So we need to talk about the speed of grinding wheels. And typically an aluminum oxide abrasive wheel, I'm going to run at basically the speed of the motor, 3,450 RPM, or lower, never higher. And honestly, I probably, most of the time, I'm closer to 3,000 to 3,200 RPM. And I'll use that for from 6 to 4 inch diameter wheels. Now, if I get into a smaller wheel, I might speed it up just a little bit, depending on what I'm doing. But generally speaking, let's just say 3,200 RPM is good for most of my aluminum oxide wheels. With the diamond wheels though, they need to go much, much slower. They need to go, I've found for a 6-inch diameter diamond wheel, 1,200 RPM is just about right. If you go too much faster than that, you're actually going to lose diamond as quickly as you lose carbide. So that's going to cost you a lot of money, and it's going to generate a lot of heat. Well, we're kind of starting like a whole new category here. These are a couple just random different abrasive cutoff wheels that I have. They're basically, like the name says, they're made for cutting something off. They're quite thin, and if you had a damaged tap or end mill that was damaged so far back it would take you forever to grind, you just cut that whole damaged end off in one shot, get her done, and then move on from there. And they do differ though. They don't really tell you what the abrasive material is on here. They explain the dimensions of the thing, the diameter, the width, the arbor size, and so on, but they really don't go into what the bond is in there or the abrasive material. If anybody knows a lot more about these and wants to give us all some more information in the comments, I mean, please feel free. I'd be interested in hearing what you have to say. When you're talking about reading the specifics on a grinding wheel, we're not going to go through all of it because there's a million different things out there, but this is a pretty typical, classical kind of grinding wheel. And I can explain to you guys what a bunch of this stuff means. So the A you see right here, that is for aluminum oxide. So the abrasive material is aluminum oxide. The 32 describes, to the manufacturer at least, exactly what type of aluminum oxide that is. The 60 that's for the grit, the size of the grit that the abrasive is made from. The J refers to the density, or you could also consider it the hardness of the wheel's ability to break down. And so that, as that letter varies, it'll make your wheel grind hotter or colder and more or less freely. The V refers to the bond, in this case a vitrified bond. It's by far the most common that I've come across is a vitrified bond. Once upon a time there was a resinoid bond. I don't know if they still have it anymore, but it wasn't the greatest because if it got wet it dissolved and people probably got hurt from that. And then here, the BE, that's another proprietary number that the manufacturer uses to identify their specific wheel. Now above there, these numbers are the diameter of the wheel, the width of the wheel, the arbor hole size of the wheel. Over here we have the maximum rated RPM of the grinding wheel. So when it comes to the different speeds, I adjust them using these pulleys here. So a 1-to-1, if I was 3 1/8 to 3 1/8, I'd be bang on 3,450 RPM, which is what the motor puts out. As this pulley gets smaller, the RPM decreases. And so this is what I'm currently using for aluminum oxide, and I'm closer to 3,000 RPM. Now when I want to run a diamond on here, I put this tiny little wee guy on there, and that's what gets me down to the 1,200 RPM. And then you can also, with this machine, you can reverse all this, and you can put the bigger one there and the smaller one here, and you can get much greater speeds by going bigger to smaller. But we don't use that for any of the examples I've shown you today. That higher speeds are used for what's called mounted points, and we're going to be going over them in a different video. This machine, on the other hand, doesn't have any way of adjusting its speed. The only speed this will go is 3,450, and so I can't use diamonds on here at all. It would just destroy the wheels so quickly, it wouldn't be cost effective. So this is strictly for, well, I use this for aluminum oxide wheels, silicon carbide wheels, and the cutoff discs. So you can actually get an awful lot of use out of a grinding wheel. I'm guessing, this is just under 3 inches now. I'm guessing it started out as 6-inch diameter. Started out as a plain wheel, 1/4 inch thick. And you can see sometime for some reason I felt the need to make it really, really thin. And I don't know what I was doing with it, but I did feel the need to do that. And they are so durable. This thing is down to 56 thou, just under a 1/16. And you can see it's got a chip out of it here, but that is not from use or from being so thin. This thing performs just fine. This was from abuse, dropping it on the floor, tapping it with a wrench. That's how this chip got in here. I would still comfortably use this today to make little 50 thou slits and whatever I had to. Now in the event you're uncertain of a grinding wheel's condition, maybe you haven't used it before yourself, maybe other people besides you use the grinding wheels, maybe you know it was dropped on the floor, anything like that. There is a preliminary test before you just put it in the machine and run it. What you can do is you can put it on a piece of wood, you can tap it with a piece of wood, and if it makes a nice ring, like that one clearly does, that means it's not cracked. If it makes a thudding noise, then it could be cracked, and you want to be suspicious of that wheel. Now I don't have one here that's cracked that'll make a thud for us, but I think you'll agree this quite clearly rings. Once you've done your ring test, it's always a good idea, again, if you're unfamiliar with the wheel or other people are using it, so on and so forth, that when you put it in the machine and fire the machine up, you don't get in line with the wheel in any direction for 1 minute. You just go off somewhere that's not in line with the wheel, you let that thing run at its speed for a solid minute, and my understanding is, as a general rule of thumb, that if a grinding wheel is going to explode from previous damage, it will do so within the first minute. Most of my grinding wheels have an 1¼ inch hole in them, and I have these little wheel spacers that take up the difference between the 1¼ inch hole here and the 5/8 diameter of my wheel arbor on the machine. And now these don't fit perfect. They kind of fall in, they flop around a bit, I think that's intentional. I don't think you ever want to press anything inside of a grinding wheel, so they make them a little small to start with. Well, the end result is when you just put it on there and snug the nut up, this wheel's really going to run out as it spins. And so what I do, just to get the maximum life I can out of a wheel, is I mark sort of the four corners, and I get opposing sides running 0 on my dial. And that way, when I do dress my wheel to make it run true, I'm wasting as very little as possible. I also do that on my diamond wheels because otherwise they'll just be, slapping away the whole time. And things running true is just a better way to go. Well, that's it for today, guys. Thanks for watching. I hope you enjoyed this. Maybe you saw something that was new to you. I'd like to give a special shout out to my dad today. He's struggling a little with his health, and so love you, Dad. You'll get there. This is all going to work out. Bye-bye for now.